Hi everybody, this is Mr. Lee. In this problem, we're going to go over a publicly available problem from College Board from the AP exam. The reason why I chose this one is I think in terms of like the amount of material and types of questions that you could see based off Coulomb's law, this is going to cover a lot of the basics that you'll need to solve any Coulomb's law problem that they throw at you. Okay, so this is a 3-charge problem. And for the sake of making it easier for us, it is a equilateral triangle. All right. To make things a little bit easier for us, we'll make the lower left-hand corner capital Q1, and we'll make the lower right-hand corner capital Q2. All right. Now, in order to start these problems, trust me when I say, the very first thing that you should do is sketch out the problem. And the reason why you want to sketch out the problem is you want to be so familiar with these problems that based off the sketch alone, you could probably predict what kind of problem that you're going to see. So for example, if I see a drawing of a 3-charge arrangement like this, immediately my mind can go towards Coulomb's law because I'm just so used to drawing these out, sketching these out. Okay, so it really does help to get that practice in. Okay, so we have a equilateral triangle. I hope it kind of looks equilateral, and all of these angles are 60 degrees, and they are all separated by a distance, a radial distance of A. Okay, so now that I sketched it out, now I can start creating models for us to use. So when I say the word models, these are just like the tools that all physicists use in order to help solve a problem. So for this one, because we're working with Coulomb's law, I know to use a free body diagram. And we're looking at the charge of this Q up there for our free body diagram. So I'm going to draw a dot right there. This is my Q, and I want to draw a free body diagram. Okay, so if I take a look at Q1 down there, I see that it's positive, and this lowercase q is also positive. So that means that Q1 will push this lowercase q away from it. And in this case, away is up and to the right. All right, so we'll call this F1. All right, now Q2, because Q2 is negative, and lowercase q is positive, it'll be attracted to it, so it'll pull Q2 down and to the right. All right. Now, on the AP exam, if they ask you to draw a free body diagram, you cannot have any components. All your forces must touch the object itself, and therefore, this right here will get you all the points. But that right there doesn't really help you out with actually solving the problem. So what I'm going to do instead is on to the right of it, I'm going to draw all the components of this charge to really help us solve this problem. All right, so I'm going to do F1 first. I'm going to break up F1 into its components. So what I mean by the components, I'm talking about the X and the Y components. So here we have F1, okay, and if I were to ask myself, okay, what direction is that force pointing? I would say up and to the right. And how do I know that is because this arrowhead tells me so. So those arrowheads are really important there. Now to create those components, all you got to do is create the same components that you just described. In this case, it'll be up and to the right. All right, so let's get some good practice in, okay, some good habits. Any components should be drawn as a dotted line, and that is so that we know that they're components and not actual forces. I can label this F1 to be, excuse me, this one is F1Y, okay, and I can label this as F1X. All right, so I have F1Y and I have F1X. Now, if I wanted to really get into the nitty-gritty of labeling it, I can use sines and cosines, and I'll do that over on my right, over here, because I'm getting a little bit crowded. All right, so if we know that F1, let's shrink this a little bit. If we know F1 is K, Q, capital Q, all over A squared, that must mean that F1Y, the vertical component, okay, we have to use our Pythagorean, or excuse me, our sines and cosines. So I take a look at this angle there, and I take a look at F1Y. This vertical component is opposite of this angle. Okay, it's not touching it. So if it's opposite, I have to use the sine function. So f1y will simply be kqq over a squared sine of theta. Now you might see this written different ways. You can see it written that way, which I think is really helpful because we're going to be plugging things into the calculator, but you can also see it written as f1 sine of theta, which is a little bit shorter and a little bit cleaner to use. All right, and so let's do the same for f1x. F1x would be f1 cosine of theta, and it's cosine because that component is touching this angle, right? So this component here is touching that angle, and if we know if it's touching it, it must be adjacent, which can be rewritten as kqq over a squared cosine of theta. All right, so we have that there. Now let's do f2. F2, if you remember, it was being pulled down and to the right. We can call that f2. Let's move f1x up there, and let's create the components. So if I take a look at f2, I am saying out loud that component is, that force is being pointed down and to the right. So I want to draw those two components. This is my rightward component, and this is my downward component. So let's call this f2x, and let's call this f2y. Of course, that right there is our 90-degree angle, and this is our angle theta. All right, and I'm going to do the same thing over here, where we can say that f2 is equal to kq lowercase q all over a squared. Okay. Yes, I know that q is negative, but when we're doing this, the signage doesn't matter because we have a free body diagram, and our free body diagram is going to help us with the signage. Okay, and we have f2y, which is, watch what I do here. If I take a look at this f2y component, it's pointing downwards, so this one should be negative f2 sine theta, or negative kq capital Q a squared sine theta, and f2x is equal to f2 cosine of theta, which is kqq a squared cosine of theta. And the reason why this f2x is positive is because it's pointing to the right. Okay, all right. Now that we have our two forces, I want to show you a neat little trick. So a lot of times in physics, things actually clean up really, really nicely. So knowing that the two corner charges are the same magnitude, that must mean that the x components and the y components are actually equal. And that helps us out with the y component here, because as you see, this y component is pointing up and this y component down here is pointing down. So up plus down, it negates itself, okay? And we can see that algebraically. So if I were to create a net force in the y-axis, we will say that we have f1y plus f2y. And if you're thinking, Mr. Lee, isn't f2 pointing downwards? Well, yes, but just wait till I substitute things in. So we can say which is equal to, so we could even fulfill this as ma if we want, right? F equals ma, but f1y is equal to, let's see here, kq capital Q a squared. This is a simple substitution from what we did before. Oh, made a mistake. All right, f1y is kqq a squared sine theta, and this one is minus kqq over a squared sine theta. All right, and I got these two substitutions from this line here and this line there. So mathematically, what happens is that this all equals to 0. Okay, so our net force in the y-axis is equal to 0 newtons. The two forces actually cancel out. All right, that leaves us with the x-axis. So I'm going to do the same thing. I'm going to create my my formula. F of x is equal to f1x plus f2x. Okay, and we know f equals ma. F1x is equal to KQQ a squared cosine of theta plus KQQ a squared cosine of theta. And if you're wondering, well, what about the negative sign? Don't worry. Remember, we're only looking at the x-axis, and both of those x components are pointing to the right. And so we're ending up with the net force in the x-axis, which is equal to ma, is equal to 2kq, capital Q, all over a squared cosine of theta. Okay, and the reason why we are multiplying that by 2 is because we have two of the same sides of the equations right there. So it just doubles up. All right, and that will be my final answer. So if we were to take a look at the actual net force free body diagram, we can say that this Q will only have a net force in the x direction. So that charge would accelerate to the right based off of the lower two, these lower two charges. Okay, and so the cool thing about doing problems this way without actually having the answers is a multiple choice problem could ask you for the net force. Okay, it could ask you about the overall net force direction given a force like that, or it could ask you about like the y-axis itself and like what happens to the y-axis. So being able to pick up on those things really does expedite your problem solving skills depending on the situation. All right, so that is I would say in terms of spice level, we got a spicy Dijon right there. Okay, it can get spicier, but that's a good amount, right? There's a good amount of spice, and it definitely brings back old memories from AP Physics C Mechanics with our vector addition. All right, so that is Coulomb's law. I'll see you next time. Bye-bye.